I'm going to talk about resilient distributed datasets. This is joint work with a lot of people in the UC Berkeley AMP lab. We have Mosharaf, TD, Ankur, Justin, Murphy, Mike Franklin, and Scott and Jan. So I think everyone is well aware of the growth in usage of MapReduce and other parallel programming models to process large data sets. But the thing that started happening soon after people loaded a lot of data into MapReduce is that they wanted to do a lot more with it. There are two kinds of things that people wanted to do that are both actually very natural applications. One is they want to do more complex applications that often have multiple MapReduce stages. So for example, things like iterative machine learning algorithms and iterative graph algorithms. And the other thing they want to do is interactive data mining, interactive queries. You have all this data in one place. It makes a lot of sense to do that. And it turns out MapReduce is actually not great at either of these. Just as a sign of that, over the past few years, there's been a lot of work in specialized programming models for these applications. So for example, Google's programming model called Pregel is designed for iterative graph algorithms such as PageRank. But we wanted to step back and see what is it that's holding these applications back, and can we solve this problem at the core. So it turns out that complex applications and interactive queries both need one thing, which is efficient primitives for data sharing. So these are both applications where you run multiple MapReduce stages that share data between themselves. And unfortunately, in MapReduce, the only primitive for sharing data across these MapReduce jobs is a stable storage, something like a distributed file system, and that's just very slow. So here's a few examples of this. At the top, I have an iterative algorithm, for example, something like PageRank, and each blue box is a MapReduce stage, and then the red pieces are data sets. And if you run this in Hadoop, you'll use the Hadoop file system HDFS as intermediate storage, and each time a stage finishes, you have to write its output to HDFS, has to go all the way to disk, it has to be replicated across 3 machines, and then on the next stage, you immediately have to read that back in and start computing on it. And so you incur this overhead in between all these stages. Similarly, if you're running interactive queries, that's shown below, each query has to incur the overhead of disk I/O to actually read this data. And so the distributed file system is slow due to replication and disk I/O, but at the same time, these things are essential because we wanted to provide fault tolerance. We don't want to lose some of the data in between our jobs and just get stuck there. So this is, it's not just by accident that this is slow. So what we want to do here is give you abstractions that let you do in-memory data sharing. So just keep the data in memory across these jobs so that you can efficiently chain together MapReduce jobs or do interactive queries, load some data into memory and do queries. And memory is a lot faster than disk. A server today can easily have 10 gigabytes per second of internal memory bandwidth, whereas most links in these large clusters are still 1 gigabit per second. But of course, it will be challenging to do this because we still need the fault tolerance that file systems provided. So really, the challenge we're addressing here is how do we design a distributed memory abstraction that's both fault tolerant and very fast? Okay. So there are a lot of in-memory storage systems for clusters, things like RAM Cloud, parallel databases, distributed shared memory. Piccolo was another system like this. But one thing that makes it hard to make these really fast is that the programming interface to them is based on fine-grained updates to mutable state. So in all these systems, you get a table of cells, and you can go read and write any cell in that table. And although that's a natural interface, it means that when you want to provide fault tolerance for these, you really have one of two options. You can either replicate the data across machines or replicate an update log across the machines. And when you have a big data application, this gets expensive because every piece of data has to go over the network, and as we just discussed, the network is 10 to 100 times slower than memory bandwidth. So how can we do then, how can we have a fault-tolerant in-memory storage system without replication? So our solution, Resilient Distributed Datasets, achieves this by restricting the programming interface. So it's restricted in two ways. So RDDs are these immutable partition datasets that you have across the cluster, and you can only build them through coarse-grained operations. By this we mean an operation that you apply to all of the elements of a dataset at once. And these includes things like map and filter and group by and so on. But what this lets us do is recover very efficiently using lineage, which is we remember the graph of transformations that were used to build each RDD. And when we lose data, we just replay some of those functions to recompute the lost data. And what's nice about that is you only have to log this one operation like a map function, not the actual data. And if nothing fails, it's essentially free. You haven't had to replicate anything. Here's a picture of how this works. So going back to our iterative job, suppose that we lose the output of iteration 2 here. The RDDs will track the lineage going back, and they'll know that we have to run this map reduce operation again to get back that data. If we lose both of these at the top, then we can go back a step further in the lineage chain and rerun iteration 1, and then rerun iteration 2. And the much more common thing is that you only lose a piece of a data set because one machine in the cluster goes down. And in that case, RDDs track lineage at the level of partitions of these data sets, smaller partitions, and they'll recompute only the missing piece by applying the part of the transformation on the previous data. Okay, so we have this restricted programming model with these coarse-grained operations. The next question is, what is it good for? How general is this? So it turns out that actually RDDs are surprisingly general. So despite these restrictions, a lot of common parallel algorithms can be expressed with RDDs. And the intuition behind this is because these are parallel algorithms, they're already applying the same operation to many pieces of data in parallel. So this strategy of logging just the operation and not the actual data makes a lot of sense. And in fact, we showed that using RDDs, we can express many of the cluster programming models that people have so far proposed as separate systems, including the kind of data flow models like MapReduce and Dryad, as well as some of these ones for iterative applications, such as Pregel, iterative MapReduce systems, and incremental computing systems. And we can also support new applications that these models don't, such as interactive ad hoc queries. Just to give some other reason why to believe this, even if you look at MapReduce today, it's running on top of file systems like GFS or the Hadoop file system that only support large writes or append-only files and large sequential reads. And despite that, despite this kind of coarse-grained interface, people have managed to do a lot with them. So to summarize, here's a trade-off space comparing RDDs to other storage abstractions. And we have two axes. We have the granularity of updates or writes, and we have the throughput of doing writes in these systems. So at the top, things like RAM cloud and key value stores support fine-grained updates, but of course they have to replicate the data over the network for fault tolerance. Hadoop file system has coarser-grained writes, but it also needs to replicate data over the network. So these systems are limited by network bandwidth. RDDs, on the other hand, are able to go as fast as the memory bandwidth because they don't need to actually replicate the data. They just need to replicate the lineage. And so these previous systems, where you have fine-grained writes, they're good for applications with fine-grained writes, such as transactional workloads, and that's really what they were designed for. Whereas RDDs, we think, are a good fit for a lot of batch applications. Okay. So in the rest of the talk, I'm going to talk about the system we build that implements RDDs called Spark, and I'll show you some examples of how to write applications in that. I'll talk just a little about the actual implementation. I want to try to do a demo, and also since we open sourced Spark, a lot of people have started using it in companies and in research in a lot of interesting applications, and I want to talk about a few of those as well. So Spark provides a simple programming interface for RDDs in the Scala programming language, which is just a high-level language for the JVM. And the interface is really modeled after Dryad Link to let you have this language-integrated programming model. Another interesting thing is you can use Spark interactively from the Scala interpreter. So this is what really enables interactive data mining. And you get a few things in Spark. You get RDDs themselves. You get two types of operations. There's transformations, which have to be deterministic and build a new RDD. And there's something called actions, which actually evaluate a function and give you back a result. And you can also control each RDD's partitioning or layout across nodes. I'll talk about why that's important a little later. And also persistence, which RDDs we keep in memory. If you want, you can also checkpoint them to disk, and so on. So let me show an example of the interface. Here we're going to be looking at how you'd use Spark interactively, and say you're operating a large web service, something is going on, and you want to load just the error messages from a log file into memory, and then search for various patterns. And this is a huge log file on the cluster. So we're going to have a cluster with a master, which is where we'll be typing our commands, and that's what does the job scheduling and the tracking of lineage for the data sets, and a bunch of workers. And the first thing we're going to type is this text file. This creates an RDD that represents a text file in the Hadoop file system. So this is a bunch of lines of text. It's a sequence of strings. And this is the base RDD. Next, we can do some transformations. Okay, so here we're calling filter, and the code in red there is Scala's syntax for a closure or lambda expression. This is how you write a function, basically. And so here you can actually use any Scala or Java code and APIs that you want. But here we're just checking which lines start with error. So those are just the errors. This is a transformed RDD. Next, we can do more transformations. For example, maybe these are tab-separated fields, and we want to pull out field number 2, which is the actual message. So we can do that with a map. And finally, we told the system to persist just the messages RDD. So maybe the whole file is too big to fit into memory, but the messages do fit. OK, so up to now, nothing's actually happened on the cluster. All these operations are executed lazily, and they really happened the first time we run an action. So let's do that. So now we're going to see how many messages contain foo, and we're going to call count. This is an action. So now this has to return a number, so we have to run some stuff on the cluster. So the master is going to look at where the data is laid out in HDFS, and it's going to send tasks to the nodes, and they'll compute and give back some results, much like in MapReduce. But the other thing the nodes will do is store in memory any partitions of persistent RDDs they've built along the way. So now these are in memory, just the messages. And so next time we run a query, maybe the problem wasn't foo, but bar, we're going to hit these that are in memory and get back the results much faster. And to give you a sense of the difference this makes, we did a test where we do a interactive full-text search of Wikipedia, which is about 50 gigabytes, on 20 machines. And with on-disk data, or with Hadoop, this takes about 20 seconds. And with in-memory data and Spark, it takes less than 1 second. So this is really the difference in interactivity and in speed you get with in-memory data storage. And we also scaled this up, so we did a terabyte of data on 100 machines, and we can do a full-text search in 5 seconds compared to about 3 minutes for on-disk data. Okay. Just to show again how does fault recovery work here, these RDDs, as I mentioned, track the graph of operations that built them. So here's the graph for the one up here. We did a filter and then a map. And they use this to rebuild lost data at the granularity of individual partitions. So in this case, actually, each RDD is a bunch of partitions, and we have a graph like this where we can recover each partition. So even if we lose one of the partitions of messages, we only have to recompute that piece of the map on that piece of HDFS data. Here's a graph with how this actually performs. This is for an iterative machine learning algorithm where we run a bunch of iterations, a bunch of different MapReduce jobs that all run over the same data. What we see here is, so the first iteration takes longer because it has to load the data from disk. Then you go pretty quickly, about 60 seconds per iteration. And then in iteration 6, a machine fails. This was in a node in a cluster with 50 machines. And we take a little longer to recompute the data from that, but not as much as the actual first iteration, because we only recompute the lost data. And then we can go on doing that. Okay. So that was one example of how you'd use RDDs interactively. The other example I wanted to show is one of these iterative algorithms. And for that, a good one is PageRank. So PageRank is an algorithm where you want to figure out the rank of each page, and essentially you start all the pages with the same rank, and then each page pushes its rank to its neighbors. It just divides it among its neighbors, and so you update everyone's rank by summing up the contributions from its neighbors. And the code for that is down at the bottom there. You don't need to really understand this in detail, but the main thing is there are two RDDs. There are the links and ranks, which are key value pairs. For each URL, you have its neighbors and its rank. And on each iteration, we join them so that we get the rank and neighbor for the same thing, the same URL on the same machine. And then we use a map to get the contributions that we add up. So this is also an algorithm where placement of data matters a lot. That's why I want to show this. So if we look at the graph of operations done here, as shown on the left, we have the links and ranks, and we keep joining these two data sets together by URL. And if you just do this naively with MapReduce, that join is going to be a shuffle of data across the network, which is quite slow. So here's where the RDD's controlled partitioning comes in. You can choose to co-partition these, so consistently hash both the URLs and both the links and the ranks with the same hash function across machines, and then that join just becomes a local operation. So the links and ranks never have to move across the network to do that. And in fact, you can even use application knowledge, like these are pages, and your pages in the same domain link to each other a lot, to cluster them by domain name. And to do that, you call the partition by operation. So just to show what effect these things have, here's the performance of PageRank on 30 machines, and we compare with Hadoop. If we just use in-memory data with Spark, we're going about 3 times faster. And if we also add controlled partitioning, we gain another factor of 3 for avoiding some of the communication. And so overall, we have about a factor of 8 speed up. This is a little less than we saw with interactive queries because there's still a bunch of communication and computation that are the limiting issues. And one interesting thing about this is the stuff I showed for PageRank, these two optimizations of keeping data in memory and controlling the partitioning are exactly what Google's Pregel does as well. So without many changes to that code, we can also implement Pregel in the same way. Okay, so a bit about the implementation. All I want to say here is we built this MapReduce engine from scratch, so it's not, say, a modified version of Hadoop, but we also tried to make it very pragmatic and compatible with Hadoop. So you can use the Mesos cluster manager, which we presented last year, to run it alongside Hadoop, and we can read from any Hadoop-supported storage system. And for the Scala language, we didn't need to actually modify Scala, although we did have to do some reflection and bytecode analysis to actually ship these functions correctly across nodes. And it is open source. And we've used this implementation also to build other programming models on top of RDDs, which, as I mentioned at the beginning, is something we can do. So you can see how MapReduce and Dryad Link are supported by essentially the interface we have already. It's very similar. But we also implemented Pregel and iterative MapReduce in about 200 lines of code. And we're working on a SQL implementation as well called Shark. And the cool thing about this is you can intermix these models in an application and very efficiently share data between them. So in Shark, for example, we're letting you mix machine learning functions with SQL queries and do those in the same program on the same in-memory data. Okay, so now I want to try to show you a demo of this actually working. So let's try to do that. Okay. All right, so what I have here, I've set up an EC2 cluster with 20 machines and this Wikipedia data set, and I'm going to do some queries interactively on Wikipedia. So let's try to do that. So first thing I'm going to do, I'm going to create this data set that's a text file. That's actually all the lines of text in this tab-separated dump of Wikipedia. And by the way, this is just a Scala console here where you can type all your Scala stuff and just evaluate expressions. But what I called here is text file builds a text file data set. So if we look at file, it's an RDD containing strings, and we can start to look at the strings already. So we can call file.first to look at the first element in that. Okay, So this is a tab-separated values file, and you can see each string, each line has actually 5 fields. Has an article ID, a title, a date modified, an XML version, and you don't see the last field, but there's also a plain text version of the article. So let's actually make a class to represent these things so that we can make them easier to work with. And this is the syntax to do that. And so here I'm just going to pull out the title and text from each article. So now we can turn this RDD of strings into an RDD of articles. And we're going to do that with some maps. So first we're going to split each string by tabs. And next, it turns out some of the articles don't have 5 fields. They don't have the last plain text field because they're things like images. Oops. So we're going to take just the ones with 5 fields. And then we're going to map, we have these fields, we're going to map them into articles. So, okay, so we take field 1 and field 4. So now we have an RDD of articles. And we can do articles that title, for example. And this is that first article, action-packed. That was the alphabetically first thing. Okay, so now we're also going to call articles.persist. To tell the system to keep these in memory after it computes them. And now let's do some queries. So let's do articles. Let's count how many of these articles mention NSDI. Okay. Okay. So let's do that. So now the data isn't actually in memory yet. So this is going to take a little bit of time, but you can see it's starting to load these article objects into memory. So this is running, on this 20-node cluster, and tasks are finishing, and it's making some progress. So let's just let this thing finish. Okay, so 19 articles mention NSDI. That's something new you've learned now, maybe. And but this took 27 seconds, which is not exactly interactive. So let's try this again now that the data is in memory. It's on the same query. And now you can see that took only about a second. So really you can explore this data interactively now. And so my next question is, there's these 2 conferences that end in SDI, NSDI, and OSDI. So let's look at OSDI. And I'll just show you can do this with variables too. So I have a variable, and now let's search for OSDI. And that's only 14 articles. So you came to the right conference. Okay. All right, so just one last thing. So we have open sourced this system, and we actually have a lot of interest from industry using it. So we have about 15 people contributing code. I know at least 5 companies that are using Spark, and we have many application projects in Berkeley too. Just one example, Conviva is doing some of its reports about 40 times faster on in-memory data using Spark. And the system builds on a lot of related work too. So I already talked about Pregel, about these specialized models and the in-memory storage systems. We're also inspired by Dryad Link. And some of the goals are similar to some of these caching systems, such as Nectar and Pacman, but these are all based on a distributed file system, whereas we can do in-memory data. So in conclusion, I've presented RDDs. They're a simple and efficient programming model that's applicable to a lot of types of applications. And the key insight here has been to leverage the coarse-grained nature of these applications to do fault recovery without having to do application. And we encourage you to play with the system at sparkproject.org.
All right, that was an impressive coding tour de force in front of a lot of people. Great. So we're ready to take a few questions from Matei. People are wowed. Okay. Yeah.
I'm Jay from MSI. So if I understand correctly, the memory ID will be out of memory if we explicitly invoke RDD.persist or RDD.checkpoint, right?
Yes.
So there will be a problem because in this programming model, do you have provided some kind of, so in the long run, especially when your job have iterations, there will be some kind of a memory leak. If we did not program in carefully.
All right, so you're saying, so that's it's a good question. You're saying there can be a memory leak if people put too many RDDs in memory.
Yeah.
So we actually least recently used a placement policy for the data in memory. So it does fall out eventually. The idea is to do the equivalent of garbage collection for you.
Okay.
Yeah, that's what we're doing.
So that is already built in the system.
Yeah, we're doing that already.
Okay,
yeah.
thank you.
Yep.
Hi, it's me, John Dunnigan again.
Okay.
So one of the benefits of doing data sharing using persistent storage is that it makes it quite easy to dedicate nodes from running tasks for one job to running tasks for another job. So I'm curious, is that a problem for RDDs? If so, how do you solve it?
All right, that's a really good question. So to leverage the in-memory data, we really have to have data locality at the level of nodes, because otherwise you lose all these benefits. So actually, all the results I showed you were with a data locality algorithm we have called delay scheduling, and essentially all these jobs had 100% data locality. So it turns out that we can do, at least with some simple algorithms, we can do pretty well there. But we haven't explored fully what will happen. Maybe in some applications this won't be the case. Yeah.
Thank you.
Okay. Any more questions?
We got one more.
Rick Farrow. So I understand that one of the things I found myself thinking is, you just mentioned there's an LRU.
Yeah.
So you're going to discard things after a while. Any thought of actually caching any of that? I mean, at first I thought, well, maybe, when you have these data sets and you run out of RAMs.
Yeah.
You're going to run out of RAM. You got to just store it at disk because maybe you're going to use it again, and that would save you recomputing.
Yeah, that's a really good question. Yeah, so when we run out of space in memory, we can either put the data on disk or we can just say we'll recompute it next time. And actually the performance is pretty good. Basically you get something in between having everything on disk and everything on memory. This is actually my first kind of backup slide because people get asked us this. But I think there are interesting memory management challenges in this kind of system, especially once you start getting a lot of users that we haven't fully looked at yet.
Okay, thank you.
Okay, let's thank Matei. Thank you very much. Great talk.